Sure, it is. Hello, can you hear me? Yes. Hello, everyone. It's Antonio Cuenca from Photonics. I'm happy to be here, and I'd like to introduce you what we've done so far with our partner, Mercedes-Benz AG Vitoria, throughout the course of this project. I'm afraid I'm not bearing good news. We're not kicking off this presentation with good news, as global temperatures are rising quicker than we anticipated. These pictures and extracts actually belong from the World Meteorological Organization and were published in May and June this year. These heat waves have knock-on effects across human health, agriculture, ecosystems, water, and power supplies. As these articles show, these global consequences are patent already, and all these articles actually are from 2022. We also highlight the result of one study conducted by the US National Academy of Sciences that highlights the growing problem of extreme heat in cities. In 2020, the UN estimated that 17% of global electricity demand was due to refrigeration, accounting for 8% of global CO2 emissions. With 3.6 billion air conditioning units, which takes the largest share of that 17%, in 2020, that number was projected to triple by 2050. That means that because and due to the urban heating island effect, which is caused by traffic, heating, air conditioning, and heat-absorbing surfaces, cities can become 3 degrees hotter than the surrounding countryside. That delta of temperature goes up to 12 degrees in hot evenings. Traditionally, we've used active solutions to tackle heat-solving problems. So we use energy to remove energy. Recent developments over the last few years pose and position passive solutions as clean and affordable alternatives. But not all in this presentation is going to be catastrophic. Let's pick up some positive vibes, shall we? So we have some tools available to us, and one of them is passive radiative cooling. It is a process that, in the process of cooling, exchanges some of the heat with outer space. It's pretty cool, right? At Cooling Photonics, we've developed and we continue developing this technology, maximizing a natural process used by Earth to cool down its surface. Some of the KPIs we achieved so far is being able to decrease the temperature of a surface 50 degrees hotter than the ambient by 20 degrees, passively, dissipating up to 250 watts per square meter. We've also been able to increase the production of solar cells by 6% and improve the performance of thermoelectric generators by 54%. Through our collaboration with Mercedes-Benz, its factory in Victoria, we pilot our technology in 3 different setups with 2 main drivers. One of them was to increase the performance of rooftop panels already installed, and to optimize how heat is managed in industrial setups. Some of the results we've been able to achieve so far throughout this process with Mercedes is being able to iterate on our product proposition for photovoltaic, improving our patterning and composition of our material, and scaling our manufacturing, setting as the basis for a future industrialization. But also in the heat management context, we've been able to cool down a conveyor motor system by 20 degrees, dissipating 17% of the excess of energy passively. No energy consumption, no maintenance needed. With regard to the absorption dryer, we've been able to cool it down by 8 degrees, dissipating passively 5% of the excess of energy. Before I close down this presentation, I would like to thank the Mercedes-Benz Vitoria team, and thank you all for your attention today. It's been a pleasure. Thanks.